So the ends are covered in hyaline cartilage, which is also known as articular cartilage. That's referring to the location. Art refers to joints or arthro. Arthro means joint, because that's where those ends are ultimately going to be within a joint. So articular or hyaline cartilage. Then within that section of the bone, right at the tips, we see that we have spongy bone. And spongy bone has within it red bone marrow. Red bone marrow is so colored because there are red blood cells being produced in there. But it produces all of the types of blood cells, red blood cells, white blood cells, and platelets. We also call this type of bone cancellous bone. So then we dive into the center of the bone. The center of the bone, if we were to cut it away, has a medullary cavity. Medullary cavity. Medulla means middle. So lots of areas of your body have a medulla. Medulla is just a location. Your brain has a medulla, your lymph nodes have a medulla, your kidneys have medulla. Just a location, just means middle. So within that middle, we see the blood vessels and the nerves. And those are the things that, of course, are making your bone alive, right? Those blood vessels are bringing oxygen and nutrients to the cells that live there. Within that medullary cavity, we also have yellow bone marrow. And because we know that it is fat, we say that that is for energy reserves. So that's a region where your bone is going to have an energy reserve for itself. So in a time of crisis or a time where you need to pull from that energy storage, you've got it in your long bones. And then if we head to the outside, we see the periosteum. Peri means around, osteon is bone. So the periosteum is a dense connective tissue layer that covers all around. You can see it in orange there, but not the tips where the articular cartilage is. That's where it ends. So that's the periosteum's location. So the periosteum, it itself also has blood vessels and nerves, and it's a site of the attachment of tendons and ligaments. So if you think about the periosteum, it itself is its own living tissue because it has its own blood supply. And it's going to be able to supply blood to that whole region around the bone tissue. Remember that bone is composed of connective tissue. All of the things we're talking about are connective tissue. You don't see any epithelial tissue up here. The endosteum is the inside layer, endo means inside. So this is going to be the layer that lines the medullary cavity. And that endosteum, that region is delicate, but that doesn't mean that it's not supportive. It is supportive. And its structure is such that it allows for bone growth and repair. Now, how many of you have ever heard of a growth plate? Growth plate. How many of you ever had yours measured? Oh, this is so exciting. Good, I'm glad. How many of you ever had it measured? You had it measured? How many of you broke your growth plate with a fracture? Well, we all heard it. That's why you knew about it. So the growth plate is situated right here. And the growth plate is known as the epiphyseal plate or growth plate. And the growth plate is an area of hyaline cartilage. It's an area of articular cartilage, just like that we see around the ends of the bone. So this is a region of cartilage that we find when you are younger than the ages of 18 to 21. But once you hit the point where you max out your growth, and it varies for everyone, of course, women sooner than men, once you finish that, 18 to 21 years old, then that region of cartilage turns into hard bone. And that's the point at which I say you can no longer grow in height. Your bones, of course, are going to always have bone remodeling or bone restructuring. But the actual length of the bone will no longer change once you have completed and filled in that epiphyseal plate. And it's on both sides. It's on both sides. But now let's talk about why we call it an epiphyseal plate. So if we were to redraw him, okay, and so this plate is located in the ends of the long bone. The ends of the long bone are called the epiphysis. Epi means upon. Epi means upon. So the epiphysis are the regions upon or on top of the region called the diaphysis. And dia means through. When you have diarrhea, it's running through you. Epi means upon. And so that's where the name epiphyseal plate comes from. So what I want to draw now is I want to take a look at the bone close up. So we're going to do a little bit more microscopic instead of macroscopic. This is very macroscopic, right? We're kind of far away looking at it like this. What I want to do is I want to take this piece. We're actually going to zoom in. You have what's called compact bone or hard bone. That bone runs around the perimeter, and then you've got your spongy bone that's running within that center. So I want to zoom in on these pieces here. So the compact bone is here. As opposed to the periosteum, which lines the outside. We're going to draw the osteon. So now you know a lot about bone, and you've just seen the long bone anatomy. So try to envision where we are. We're going to be at one of the knobs, if you will. Pick a knob. That's what we're going to zoom in on and see what this osteon looks like there. So we're going to start with a circle in the middle, and then tiny circles around the outside. So I'm going to make a couple of rings, just so we have a little bit more of a view of what we're looking at. Remember to make them as rings. We call them concentric rings. And so put those circles, backtracking from the center, right aligned with each other. And we're going to start to connect these rings like so. And we're going to continue to connect them. Showing the true ring. That's exactly what an osteon looks like. It's got all of these rings, and the rings, of course, have names. So all of the white space in between the rings are called lamellae. Again, we are looking at a small portion of one of those outer knobs of the long bone. Try to picture where we are. If we were Magic School Bus and I took you on a field trip and I shrunk you down really small, that's where we would all be standing, right on one of these knobs, right here. We're going to be here, okay, right there. And right now, we're actually about here. So now, let's label some of these pieces, all of these interconnections. I'll label up here, so I'm running next space. These are called canaliculi. Canaliculi are little tunnels that allow the cells that live in the bone to get nutrients. Okay, the canaliculi are these little tunnels, these little channels that interconnect the cells to allow for nutrients to be transferred. So where are the nutrients coming from? Well, the nutrients are coming from this centerpiece. And within the centerpiece, we find three things: artery, vein, nerve. Artery, vein, nerve. So blood vessels and nerve. So that's where the nutrients are coming from. So that centerpiece is a very vital part of bone tissue. It's a very vital part of this picture, which is an osteon. And the osteon, let's describe it now as the structural or anatomical and functional, so doing a job, unit or portion of compact or hard bone. Cortical, okay? Structural and functional unit of compact or hard bone, cortical bone. Cortical bone is hard bone. So when you look at hard bone, you will see many of these individual osteons. And the major component, along with the matrix, which is a little bit interspersed with these little circles, let's put some of them in there, are these cells. And you could make as many or as few as you like. If you make a couple, you get the point. And they are living cells. They're absolutely alive. It's another thing that allows bone tissue to be alive. Bone is a living tissue. It can bleed if you were to fracture it. And now you see the source of the blood. And it will hurt when you fracture it. And you can see the nerve. So these pieces are osteocyte, bone cell. Osteocyte, bone cell. And they have these extensions, so they look like little bugs as we draw them, these extensions. And those extensions are extending through these canaliculi. That's where those projections come from. All of those cellular projections allow the transfer and share of nutrients. And then these osteocytes are living in the lacuna, which is a chamber. It's a section of space where they live. So this canal is called the Haversian or central canal. And it is that central canal that houses the blood vessels and nerves, which supply the nutrients to the bone. So what we're going to do is we are going to take this picture and I'm going to make a teeny tiny little version of it and then just show you some other feature of this. So basically right now we're looking top down, so a bird's eye view. We are above the osteon and looking down into it. I want to take it and turn it on its side. So you're looking at it from a side view. Does that make sense? Okay, so we're just going to take this and draw it here, and we're going to draw something that looks like this. Almost like a pie, a piece of a pie, just so we have a side view. Does that make sense? So it's a side view of this. This is the top, the triangle shape is the top. This is the side, so like a slice of pie. Okay, and this piece down here would be like where the innards of the pie would be, and this would be the pie crust.
all I want to draw here is a couple of osteons, like so. And specifically, I'm drawing the central canal and leaving it at that. So to prove it's the central canal, let's throw some blood vessels in there and some nerves, just to remind ourselves, well, we're looking at a Haversian canal. And in that canal, since that's the top-down view, that canal runs through the tissue. Theoretically, we did like dotted lines. You don't have to do this to mess up your picture, but if you went like this, the canal would extend down on the side. On the side here. Can you picture that? Can I see the angle we've got? And we have connections between central canals. So way down deep into the bone, you can find additional connections. And this is an additional connection. So those additional canals are called Volkmann canals, or chambers that allow osteons or central canals to share nutrients. So this is a chamber that connects central canals to each other, other central canals to each other. Because the last thing I want to draw is spongy bone. So if we go back to this picture, remember where we are. We were here a moment ago. Now I want to extend our picture right like that. Okay, so if we do that, this piece is where I highlighted in orange. Then we're going to draw right in this piece. So this part here, let's make like a notation just to show ourselves it's separate. Although there really isn't a line of demarcation. There really isn't one. It doesn't exist. But we'll just make this compact bone or hard bone. And now I want to draw spongy bone right here. So spongy bone is the area where your body makes red blood cells, white blood cells, and platelets. It's where hematopoiesis takes place. And it looks exactly like you would expect. It's got all of these holes or pores that have connections to each other. Hold on, it just froze. Okay. All of these connections. Like so. And for those of you who did OP or osteoporosis, these pores become a lot more numerous and larger in osteoporosis. The spongy bone and hard bone, you start to see a lot more porosity, a lot more space, which of course leads or lends to the bone being very fragile and fractures coming more frequently. So this is spongy bone. So we call this trabecular bone because it's filled with trabeculae. Trabeculae are those little pointy sections of bone that intersperse. All of these are pores. These are the holes. And then all of these leftover bone, it's hard to show it to you, all of the regular bone, trabeculae are the pointy bones, and then these are the pores, the holes. So the trabeculae, just like osteons, are the anatomical and functional unit of hard bone. Trabeculae are the structural and functional unit of spongy bone. Structural and functional unit of spongy bone. So I just taught you two things. Try not to lose track of the basics. Osteons are the structural and functional unit of hard bone, and trabeculae are the structural and functional units of spongy bone.
The spongy bone is made of trabeculae. Hard bone is made of osteons. I want to show you different types of bone cells. So we'll make a long bone. The first type are osteo. They look like little cubes, and they live on the outside of the bone. They, of course, have a nucleus because they are living cells, and these are osteoblasts. And osteoblasts build bone. So B for B. Okay, osteoblasts build bone. And they are triggered by a hormone called calcitonin. They are triggered by a hormone called calcitonin. That's what triggers them to become activated and build bone. When they do that, they're going to pull stuff from your blood and then lay it onto your bone. So you're using hormones and bone cells to regulate the levels of calcium in your blood. Then we have another cell. And these cells are huge, and they're multinucleated. And these are called osteoclasts. And osteoclasts catabolize bone. So to catabolize means to break it down. So osteoblast and osteoclast do the opposites. And osteoclasts are triggered by PTH. TH is a hormone called parathyroid hormone. It is the opposite of calcitonin. These two cells are direct antagonists of each other. One is helping to build, one is helping to break. So PTH puts calcium back into the blood. It's going to pull it from the bone. So the last bone cell lives inside of the bone. It lives in the osteons, and it's the one you know well. Osteocyte. So it's going to regulate a balance between the two cells, which are building and breaking bone, building and breaking bone, building and breaking bone. These cells ensure that your bones remodel appropriately and that their shape is appropriate to what your body needs. In addition, an osteocyte is nothing more than an osteoblast that's encased in the bone matrix. So osteocytes and osteoblasts, the one in blue and the one in orange, are the same cell. But we give it a new name based on its location. If it lives on the outside of the bone, it's a blast. If it lives buried in the osteon, in the hard compact bone, it's an osteocyte. They're the same cell. And your body has lots of examples of this. When we talk about the blood cells, we will talk about a blood cell that has two different names depending on its tissue type, where it's living. So we give things new names. Now, it's not just that we give it a new name, it also has a new function and a new structure, right? An osteoblast doesn't look very much like an osteocyte. They keep change structure depending on their location. But it is essentially the same cell. Location is changed.
So anyway, so let's move on. I want to do the very last cell, and I'm going to choose yet another color. So osteoblasts build the bone, particularly like even if you think about when else would we build the bone, not just for growth and maintaining the shape, but it can fracture a bone. It's the blasts that are going to come in and fill in that gap and fix that fracture. Osteoclasts are going to metabolize bone or resorb. Resorb means to pull it back, to take it out. And then osteocytes are the ones we've been learning about since histology in chapter 4. Those are going to be the cells that live within the contact bone. They live in the matrix. And they actually do a balance. They do some regulating between osteoblasts and osteoclasts to ensure that we have the right balance of those, and also that the bone is maintained, the bone tissue is maintained. That's the only cell that is first of all, it's the most abundant bone cell, and it's a mature bone cell. An osteocyte is nothing more than an osteoblast that has matured. So an osteoblast is an immature bone cell, and an osteocyte is an osteoblast that's grown up, now grown up, and it lives embedded in the matrix. How do we get those? So they come from what's called an osteoprogenitor cell. An osteoprogenitor cell is a cell that creates bone cells to progenerate. Think about the gener in there, the generate, to generate or create. So this is a cell that creates bone cells. It's a stem cell, and it's a stem cell that makes bone cells, hence osteo. And the cell it makes is an osteoblast. So osteoprogenitor cells, they are with a single nucleus. And their job is to create an osteoblast, which will then mature and become an osteocyte. An osteoclast is made in a different way. We won't even bring that one up. So what I want to do is I want to talk about how our body regulates calcium in our blood. But I also want to talk about the functions of calcium. Most people think about it for bone, and then they stop there. But there's more than just that. And I want to talk about what happens if the calcium is not regulated and you have too much calcium in your blood, right? Because you know, anything in excess can be toxic. Anything. We're going to draw your thyroid gland. Your thyroid gland is near your voice box. And glands are epithelial tissue. Remember we learned that? So they're very soft. They're squishy. They're not muscle. They're not connective tissue. They're glandular tissue, which is epithelial tissue. So their texture is different than a lot of things you think of. They're soft. So that's your thyroid gland. And then living within the thyroid gland are parathyroid glands. These two glands work in conjunction to regulate your blood calcium level. So this is a perfect time. Why do we need calcium? What is its job? What are the functions of calcium? Why do we need calcium? So we do need it for bones, and we need it for teeth, which teeth are not bones. Teeth are not bones because they don't have collagen, but there's so much more. So calcium is also required for blood clotting. If you don't have the appropriate amount of calcium in your blood, you cannot clot your blood. You will bleed out. Very surprising to people, right? You think about how you make a clot, and you think there's so much involved. It's actually called a clotting cascade. There are many, many factors for clotting. Many. This is just one of the many. And in any of those sequences, in that whole cascade, if anything goes wrong, you may not be able to make a clot. We need it for nervous conduction and muscle contraction. Without calcium, you cannot contract your muscle. If calcium is not present in your muscle cells, you cannot move your arm. You could not blink. You could not breathe. You would be unable to contract the muscle.
Calcium has a ton of functions that a lot of people don't know about. Now what I want to do is I want to draw a long bone. Then I want to draw the cells that we drew yesterday. Got one there, and I'll put one here. Okay, and they've got, as you know, more than one. Osteoblasts build bone, very good. And osteoclasts catabolize bone, very good. Your textbook will say break down bone, but I love to use the word catabolize because we know it means to break. And then it's C for C, B for B, and C for C. It makes perfect sense. Or resort. The word resort means catabolize, to bring it back in, to take it back in. All right. So then I want to make some blood vessels because we're talking about how does your body regulate blood calcium level. So we need to see the blood. So we got some blood vessels there. There are two hormones involved. So let's start with the hormone in the thyroid gland. So we're going to take an arrow and bring it from the thyroid gland to the osteoblast. We're going to label that hormone. And it's called calcitonin. I'm going to write it up here so it's bigger. And I want you to think of this hormone as this. Tone it down. Someone told you to tone it down. What do they tell you? Calm down. Bring it down a notch. So if you hear calcitonin, you're toning down the blood calcium level. That means you are taking calcium from the blood and you're toning it down. You're bringing the level in the blood down. And where are you going to put the calcium? You're going to put it in the location where we store calcium, which is the bone. So osteoblasts are triggered and activated by calcitonin. Calcitonin, will take the blood calcium level and tone it down, bring it down, decrease it, lower it by taking the calcium and adding it to the bone tissue. So now you can imagine if these two hormones work antagonistically, if these two hormones work in conjunction with each other, the other hormone we're about to discuss isn't going to lower blood calcium level, but instead it will be raising it. Very good. And now we're going to go from the parathyroid gland. This hormone is PTH. Parathyroid hormone, PTH. You're going to think P for the plus sign, or adding. So we're going to add calcium to the blood. So parathyroid hormone triggers or activates osteoclasts. And osteoclasts catabolize bone. They take the bone and they break it down, which means they're removing calcium from the bone and they're going to add it to the blood. These two hormones work antagonistically. These two hormones work in conjunction to regulate your blood calcium level. Little up, little down, little up, little down. They keep it regulated all day. You need calcium for blood clotting, nervous conduction, muscle contraction, and of course, bone structure. Let's talk about too much calcium. We already know what too little does. No nervous conduction, no blood clotting, brittle bones, right? We understand the deficiency of calcium. But what about too much calcium? Stones. Kidney stones. Then we like to say, you'll get this in a minute. Bones, because your bones can ache if there's too much calcium. So the bones can have an ache. You know, like this kind of bone pain, deep bone pain. So stones, bones,
kind of see where I'm going. Groans, which refers to fatigue. If I ask a student, oh, how are I'm tired, right? They groan. Everyone groans when they're tired. I'm tired, right? It's a classic. How do you feel? I'm tired. You will groan. Then we have moans. So moans is constipation. If you're constipated, you're sitting on that toilet and you are moaning because it hurts. You're passing a rock. And the last one is thrones, the toilet. Because you would have polyuria. You are peeing a lot. Poly means much or many, and urea means urine. Very good.